Welcome back to video 2 of the Introduction to Thermodynamics by the International Consortium of Advanced Technologies and Security. So here we need to ask ourselves, how do the laws of thermodynamics relate to thermal imaging, to the field of thermography? Why do we need to understand them? We need to understand them in order to fully grasp what is happening in the various types of devices or uses we put forward in the field. How the heat is generated, how it gets to us. In the image you're looking at, we have a power supply and a sensitive piece of radio equipment, which, since it both sends and receives a signal, the power supply itself can interfere with those signals, the interpretation of them, in the various forms that radio waves are used, just by having an issue with the rear contact. In this case, the issue would be the power, could be power supply failure if it's allowed to go to failure, and then of course that would cause equipment failure because the power is gone. This is in an air-conditioned space, and so nothing seems hot as you walk past. You don't feel the radiation coming off of this device, but the infrared, the thermal imaging device can see it. However, we can spot this problem, and this problem was immediately repaired because of the high priority and importance of this piece of equipment. In this space, there were a number of these that were corrected immediately. But what is the issue? Your clue to answering this is that the fan motor to the upper left in the image is generating heat. That's why it looks hot to you, because it is pushing air. So it's doing work. Second law of thermodynamics, a little bit of energy or heat is always lost in every energy transaction, and here you have, in essence, an air pump or a fan that is moving air, and air is a fluid, it has weight, therefore it's putting out energy, it's burning watts, joules are being expended, turned into, expressed as energy of air being moved, and so you have heat being generated, and this is normal. The real issue here is the hot contactor, where the red arrow is pointing. Practice in the field with your level 3 instructor will show you how to tell the difference by attenuating the image that you're looking at. Here are 3 images of the same motor. Left to right, this is what we call a real-time or an actual visual image using visual light range. The infrared thermograph that is used in the report, and then a picture-in-picture image of the same device. And the picture-in-picture allows you to see in context what the problem is and exactly where the issue is. It focuses your attention much like the red arrows would for the technician that goes back to repair these. So thermodynamics is taken from 2 Greek words, therme or heat, and dynamis, where we get dynamite or dynamo, meaning to move, dynamite, strong, powerful, strength. Okay, lots of uses for that. In English we have a much larger vocabulary and than any other language actually in the world, twice what the next one is, and that's German, which this is based on. But so dynamis, dynamo, we use it to indicate strength or power. So those thermodynamics it's kind of easy to remember, is the movement of heat. It's accurately remembered that way also, but it is the branch of physics dealing with energy transformations from and into thermal energy. Engines use fuel for energy and so must make and then lose heat. But they will all have rules that tell you if this is normal or abnormal. You know, a diesel engine is going to have heat, and then you're going to have heat as it removes it, and through its various ways of venting that heat out. If the heat's somewhere else, or if one of the cylinders is not hot, then you have a different kind of problem. You have to analyze each of those issues. In mechanical systems, they are governed by Newton's laws. Heat is usually indicative of a problem because the internal energy of the system and its ability to work well and efficiently depend on how low the friction is, how low the resistance to movement is. In electrical system or electromechanical systems, say the motor, like you can see here, the motor heat can be a normal byproduct or an abnormal byproduct that is a problem. If you block physically, hold your hand up and block the bottom part of the thermal image there, you can kind of get a grasp, or at least mentally block that. You can get a grasp of what the motor should look like under normal conditions. The only thing abnormal here is the front of that motor. We'll deal with this particular one later because it's important to understanding lubrication and why ISO standards are what they are and how they're made and created to prevent the lubrication failure, which would cause bearing failure, which would cause motor failure, which would cause the device it's driving to stop working. In the electrical system, which you'll see pictures of in a minute, the heat is almost always a problem. The exceptions are transformers, resistors, relays, coils, and lights, light bulbs, incandescent especially, which all give off heat of their own, and they are supposed to. A light, of course, gets the energy excited enough to be able to be given off as a visible light that's quite warm as far as thermodynamics is concerned. But transformers, resistors, relays, and coils always have heat, and if you're looking at, let's say, a motor controller, you're going to have some relays, resistors inside that, and heat is normal in those cases. In thermodynamics, we think about quantities, which describe the system we're looking at. Volume, temperature, the pressure of gas, tell us about the system and the work it can do, etc. Electromechanical systems do work and therefore have waste heat, which is not necessarily an issue, except it might be an environmental issue, that is, how hot the area is, or the efficiency of the machine itself. It could be wasted heat, wasted energy that gets into the environment and needs to be removed, or it might be an inefficiency that the machine is experiencing. But in thermal imaging, we're dealing with what is hot, why it is hot, where the energy is coming from, and how did it get into our imaging device. So it's necessary to differentiate between heat that is normal and heat as an indicator of a problem. And so this is a qualitative issue as well. Thermal energy is that particular energy given off as electromagnetic radiation. Until that is emitted as radiation, that same energy was kinetic energy, literally molecular vibration. Friction is a good example of this. If you rub your hands together real briskly, they'll warm up. We do that on cold days and such. Boyle's law, in a fixed amount of gas at a fixed temperature, pressure, and volume are inversely proportional. In most bodies of mass, that energy is given off as infrared radiation. Here's a principle. Short wavelengths of light, say UV light, ultraviolet, has more energy than long wavelengths of light, say infrared. The application is, turn on an incandescent light bulb under low power. This is kind of a proof of that. At first it becomes hot, giving off infrared light, and a thermographer can see that even though you might not be able to see any visible light. It's being given off as infrared. Turn that power up, and those red wavelengths shorten into the visible red range. It glows red and you can see it. Turn the energy up a little bit more and the light given off turns towards yellow. This is warm yellow light, in other words, or warm white light. Some warm white incandescent bulbs, if you can find them anymore, are in this range. They're a yellow, a white light shifted towards the yellow. Add even more energy, and the light given off has shorter wavelength. It has moved into the cool white or into the blue range as the filament becomes hotter and the wavelengths get shorter. Let's review the 4 laws of thermodynamics. The 0th law of thermodynamics states that between bodies of different temperature, heat will always flow from the body of higher temperature to the body of lower temperature until the temperature of the two bodies are the same, or they are in thermal equilibrium. The corollary to this law is that if two systems are in thermal equilibrium with a third system, then they must be in thermal equilibrium with each other. So this is the first law of logic. A equals A. course, it applies to everything. So if block number 1 is in thermal equilibrium with block number 2, and if block number 2 is in equilibrium with block number 3, then it's necessarily true that block number 1 is in thermal equilibrium with block number 3. At thermal equilibrium, there is no energy left to do work between those bodies, and so zero work is being done between them. Zero energy is being transferred. The first law of thermodynamics can be stated thusly: energy in a closed system is a constant. It is not being created or destroyed. Rudolf Clausius in 1850 stated it this way: in a thermodynamic process, the increment in the internal energy of a system is equal to the difference between the increment of the heat accumulated by the system and the increment of work done by it. For all adiabatic processes, that is, where no heat is being exchanged, between two specific states of a closed system, the net work done is the same regardless of the nature of the closed system and or the details of the process itself. The second law of thermodynamics states that the entropy, or the disorganized energy in a system, the entropy of an isolated system which is not in thermal equilibrium, always increases. Many ways of stating both of these laws, all of these laws. One is energy always flows down a thermodynamic gradient. That's my favorite aspect, actually. Isolated systems spontaneously move towards thermal equilibrium, the state of maximum entropy of the system in a process known as thermalization, and so heat is flowing from the higher energy system to the lower energy system, trying to reach equilibrium. Heat and work are forms of energy transfer. That was Joules's law also. So, the third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches zero. In other words, the entropy, again, if it's flowing down a thermodynamic gradient and the gradient is getting smaller, then the entropy, or the change in the available energy for work, is dropping. But as it approaches zero, and that's 0 Kelvin, so that's absolutely having no energy at all. The entropy of a system at absolute zero is typically necessarily zero. In all cases, it is determined only by the number of different ground states it has. A little bit hard to measure it without that idea. Theoretically, no one has actually been able to get anything to 0 Kelvin, nor find anything that is 0 Kelvin. But in theory, when they're trying to calculate how much energy has come out of the system, how much is left, they claim to have come very close to 0 Kelvin. It's a little bit hard to measure. You can't. There's no metric that you can do. It has to be a calculation, and this is one of the reasons. Specifically, the entropy of a pure crystalline substance at absolute temperature is zero. Again, this is theory. It's never been proved. It's never been measured. It's very hard to get something to that energy state of 0 Kelvin.